Okay, hello everyone. So this is the third lecture. We are like 1 hour and a half. We will be in the middle of the lecture. So let's see where we are. So we have seen what is a quantum computer from a computer scientist perspective, which means how to simulate it. We have seen tensor networks, and we have seen the first algorithms to actually simulate quantum computer on tensor network. But we have not implemented it yet. I mean, some of you have started on some result, but that would be the job maybe for this afternoon or maybe tomorrow, depending on whom. On yesterday, I started to introduce how we can use SVD to actually get a low rank approximation of a matrix. And that's really the crux of tensor network. So now, from now on, everything we will do will involve at some point some truncation of low rank matrices, and it's really linked intimately to entanglement. And so essentially, it means that these techniques work very, very well for systems that are not too much entangled. Maybe actually before we leave this, so today I'm going to explain essentially all the remaining algorithms, all the remaining class of algorithm in the context of quantum computers. So we will see the DMRG, density matrix renormalization group. Be aware that the one you will see today is the DMRG for quantum circuit, which is not at all what people have in mind when they think about DMRG. When they think about DMRG, they have in mind something to find the ground state of a many-body system. So this we will maybe see today, if I'm fast enough. Anyway, it's almost the same algorithm. There are like 1 or 2 steps that change at the end, but all the DMRG algorithms, they are very, very similar in nature. So we will see that. And then we will have, I think, a complete tour of the classes of algorithms. And then we will leave that, and we will leave quantum computing to look at many body system a bit. So this transverse field model that I mentioned. I think I will have time to do it today. And tomorrow we will start with a completely different class of algorithms, so the tensor cross interpolation. And this is much less well known. So if you discuss with people that have known about this, all the beginnings, they yes, yeah, sure. Tensor cross interpolation is still a handful of people know about it. But I believe that it's an algorithm that is here to stay, and that's going to actually change a lot of things in the way we do inference. You will see by yourself. It's kind of amazing. It is on yes. Yeah. And then we will use that once we have TCI. We will have the tools we need to do partial differential equations. So that we will end with this at the very end. Just a note: if you fail to simulate something with tensor networks, like for instance a quantum computer experiment, it doesn't mean that it can't be done. There are other class of algorithms. For instance, if your quantum circuit only have Hadamard control node X, Y, Z, then you have an algorithm to simulate that, which is super fast. It's called, because this belongs to the type of gates known as Clifford gate, and you can simulate that in polynomial time, and you get super highly entangled states. But since everyone stay on the XY axis, it's actually you can simulate it in polynomial time. And people do that a lot when, if you want to simulate quantum error correction, for instance, you need to simulate a lot of qubits, and it's a way to do that. With, of course, the drawback that you have a very simple noise model that is compatible with these gates. You can have this. You can have quantum Monte Carlo. So quantum Monte Carlo, I wanted to include it. I wanted to include it initially, but okay, I just at some point I realized that you can't do everything. But quantum Monte Carlo sometimes work where tensor network don't. There is a big revival of quantum Monte Carlo now in the context of AI. You can essentially write your variational wave function in terms of deep neural network circuit. And so it's a field that is growing quite quickly. And there are also things at the intersections. For instance, in my own research, I work with things that are kind of halfway between tensor networks and neural networks. And I could continue like that forever. You can use Feynman diagrams, ways to calculate them, bypass entanglement barriers. So something cannot be simulated with tensor network. Maybe it can be simulated in a different way. Essentially, whenever you manage to simulate something on your classical computer, it means that you have found the structure of the problem and you are trying to harvest it to simulate it. And there are many structures, not only the low entanglement one. Okay. I had a question from Christophe, actually, and that I'd like to make a remark. So we saw at the end of yesterday that I calculated the reduced density matrix for a system with that you split into two. You can do that on an MPS. So if you have an MPS, so this is your wave function. This is your wave function. If you want to make the density matrix, you're going to make two copies of it. Sorry, that would be type psi. And if you want to now integrate over the A part of the system, so let's say this is system A, system B, well, then you realize that I shouldn't have put my legs facing outward. But okay, then you need to just integrate like that. So actually, usually it's written like this more. Like this, don't join, right? And you have seen already in several of the contractions that I've done that when you have something like that, you contract here, and then you continue until you get essentially something like that. So this is a reduced density matrix, rho B. And this guy here is called the environment. Because essentially it contains all the information you need to know about A to have the density matrix about B. And in all the algorithms that, I mean, also that we have seen already and that we are going to see later, you always keep track of the environment. Typically, you just calculate the environment. You can calculate it different environments depending on whom you integrate out. Sometimes you also start from the bottom, get a list of them, and then you can calculate pretty much everything you want. Okay. Okay, so the first thing I need to, I mean, I need one more concept before we can actually revisit the MPS simulator and start to compress. And this concept is a concept of canonical form. So when you have an MPS psi, which I show that one way you can write it is like this, like a matrix that depends on M1, A2, I2, IN. Right, this is just, I wrote this equation already. This is not unique. There are many MPS that correspond to the left-hand side. On this you can see very easily, for instance, I could insert here, like I take a matrix U minus 1, this is identity. And then I define M1 bar equal M1 U, M2 bar equal U minus 1 M2. One. Okay, and it's the same left-hand side, but different matrices. So you don't have a unique way to choose your matrix. Which means, and it's like when you do, it's called gauge freedom. In analogy with electromagnetism, where you also have different vector potentials that correspond to the same electric field or magnetic field, right? Also, on the same way as in electromagnetism, we actually typically choose a gauge, and we are going to choose a gauge depending on the problem. Some of them are more suitable than others. We can choose whenever we want. There are canonical gauges, canonical choice, and I'm going to introduce one of them now, and maybe a second one tomorrow, time allows. So the canonical form. I was going to answer a question that I had, I think the first day. Why do we use QR? I mean, where do we put the Q when we put the R? And it didn't matter so far, but now it's going to matter. So canonical form is this. You start with an MPS, any form that you have, and you perform a QR. I cut the here. I put the Q here and the R here. Okay. So I get Q, R, and then the rest. One, two, three, four. Oh, sorry. Before we do that, we are going to decide on what is called the orthogonal center. So let's say we want this guy to be the center. So we will, okay. So now, next, I absorb the R with the next one. Just sending the R to the next. Okay, so now I am back to something like this. And I do, again, now I cut this one. And look very carefully where I put the line. I cut like this. So I take the physical line and the virtual line on one side, and I put the Q here and the R here. And I get Q, another Q, the R, and the R, I absorb it in this star, star R. Okay, and that's it. I am done for the upper part. And now I'm going to do the same thing from the upper part until I reach the star. And now be careful also so now here I cut like that. Now the Q is below and the R above. Okay. I take the R, I absorb it here. And then I cut again like that. Q, R. You see the one way and the other way. And I get the canonical form. That's it. So pretty much whenever you have an MPS, you just don't think, you just put it in canonical form. If you don't know why, usually a bit later you will realize why. Okay? So it has a lot of nice things. First, you see, you send the R toward the center each time. And the R contain, and when you have a matrix and you put it in QR, Q is unitary. So and the R contains all the eigenvalues on the diagonal, right? The triangular matrix. So you're sending all the numbers that may be big or small, all to one place. And then maybe the big one will compensate this by a small one, or maybe you have too big, so it becomes very big, or too small, and then you can just ignore it. But at least you put all the information in one place. Very important to do that. When you have one, so on everything now is well normalized. You don't have like super giant numbers. Or everything is only thing that can be small or big is here. That's one reason. Second reason is that, well, now these matrices, they actually are unitaries, and we are going to use that. So if I take the first one here, and if I contract it with itself but a mirror, well, it's a unitary matrix, so I just get identity. Okay. Now, if I take the second row, it corresponds to the first row. If I take the second row, I get Q. I contract it with Q star. Not like that. So I need to have also like this. Well, then since this is a unitary where these are the rows and these are the columns, this is also identity. And same for the bottom one. But in the reverse order. One. Okay. And oh, okay, actually, they would make good use of this. Oh, I erase it. That's very handy. Suppose I want to calculate this density matrix. And I have put my orthogonal center here. Well, the first one, I can contract it, and I have nothing to do. Two, three, four. 2, 3, 4. The first one, I contract it, and I have nothing to do. Then the second one, same thing. So it's equal to that. And then the next one, same thing. And same thing. That's it. Nothing to do. Remember also when we this algorithm for sampling NPS. For sampling, we needed also to calculate the environment. So if you put it in canonical form, you have actually nothing to do. Just have to take the matrix and that's it. Okay, so it's really very, very handy. You can just okay.
Basically, what you're saying that once you trace out the bot,
yeah, it corresponds to diagonalizing the bus.
Yeah.
Put the bus in an orthonormal basis, and therefore you just have you can trace it without doing anything.
Comparison bot and it's a mixed estimated for that. So what type of information will we have in there?
I get you.
I mean,
I just rotated things a bit, so it's I've really done nothing. I lost no information. Just so far.
Yeah, that's I that point, but somehow I want to. So initially the matrix was here, but now you do this partial trace and you get a mixed length.
Yes.
So the information about the mixture is now in the star.
So the information about the mixture has always been here. So when I trace this out, if I don't do canonical form, then I have this environment, right? And now if I diagonalize this environment, I could just send the eigenvalue here, and that's it.
So the density matrix of the environment comes unitary, no, not unitary, but identity matrix.
Yes.
Yes.
No, yes. I mean, you have sent the singular values here, so they are somewhere. Huh? But so bottom line is that if you look at your MPS and you find that the bond dimension here at one link is 1, it means that this is a product of this with that. So the two separate, and then there is no entanglement between the two. You can trace out one without affecting the other, formulating the same thing.
Before the orthogonal is in the middle. Is a numerical reason for doing this? That it's kind of more stable numerically.
No. In practice, we
put it there because of physical reasons, so to say, but above in the MPS.
Yes.
You put it also at the end, right?
The center.
Center.
So the center, we are going to move it. We are going to move it a lot. So it's never at the same place. And typically, in the DMRG algorithm that we will see now, we are going to optimize one tensor, and this tensor will be the one where we put in the center. And this I'm going to explain now.
Say before that all the information is contained in the dark bound.
No, not all information. You still have some information in all the matrices, but all the others, they are unitaries, which means that they are, the only eigenvalue that they are allowed to have is on the unit circle. So everything is well controlled, I would say. It's a well-behaved matrix, a unitary matrix. It cannot have, yeah. No, this is exact. This is exact at this stage. It was the last bit that I needed to start the compression. And this is what I'm going to do now. Before I do that, suppose that you want to calculate the norm. You want to calculate the norm of your MPS. Then this is just equal if this guy is, in this case, M3, alpha, beta, I, alpha, I, beta. Then everything, so this is equal to the star, to that. Means that it is equal to sum over alpha I and beta of M alpha I beta square. Very efficient way to get the norm of your vector. So you have to work a bit because you have to do QR. If the matrix is chi by chi, QR costs you chi to the cube, but with a small prefactor. So QR is always preferable to SVD. It's typically 10 times faster. But then at the end, many of the calculations become trivial. Okay? And now we can compress. So is it clear what we have? Canonical form is just a way to fix the gauge in a way that the MPS is a more convenient form where some of the things we get for free. On the what I want to show now is that using the canonical form, and if we do the SVD of this star tensor, we get the SVD of the MPS seen as a huge matrix. So let me be a bit more precise. So I have my MPS in canonical form. So sometimes you will see, if you read papers, people they want to indicate who are what is the direction, how it was cut. So sometimes you will see, for instance, this one written like this. Okay, but it's clearer maybe, but I find it a bit ugly. So well, once you know, I mean, it's always the same thing. So it's but here, this actually at one indication that it really shows where it's pointing to, which means it shows that this is a unitary matrix when you consider this on one side and these two on the other side. So this as a row, this as columns. This as a row, these are columns. Okay. If you don't have this kind of notation, then you need to remember what you have done. Anyway, now we do a SVD of this guy. Okay. So it's lambda u d q good point. When I do SVD, I need to say whether I do it like that, for instance, or like this. So let's say I do it like that. If I do it like that, then the U gets the physical leg. U. Okay. Now, if I see this MPS as a matrix where these are the rows, and those, no, sorry, those are the rows. Well, it doesn't matter. And those are the columns. So it's, you see, you can really consider as a matrix. You could put the flattening thing if you want. Then this matrix here, this is equal to that, same thing as before. So this matrix is actually unitary. So I could call it, I don't know, like big V, for instance. And this matrix, for the same reason, is some unitary here. So it means that I have written my MPS as big U, lambda, big V. So actually, I have an SVD of the full exponentially large tensor implicitly, written in terms of all these small tensors. So I know now I know how to do the correct compression of this as a low rank matrix. I just need to, if I want to have a compression with rank chi, I just keep the chi biggest singular value of this guy. You see what I have this property because it is SVD of the exponentially large matrix, right? So this is what I meant by I said, oh, I send all the important information toward the center. You don't do that. If you do an SVD of something in the middle without putting it in QR, you're just throwing information, but you have no way to say that it is a good approximation of the thing. On most of the time, it won't actually, because you are maybe you are okay. Singular values that you are throwing away is small, but maybe it's multiplied by things very big on the outside, and you don't know anything about what is going on the outside. So you need to get information from the environment down to where you are actually doing the calculation. Okay. So if you are given an MPS by someone and you want to compress it, the first thing you do is you put it in QR. You put the orthogonal center, let's say, at the bottom. Then you do an SVD of this guy. SVD actually can allow you to I said you need QR to put in orthogonal center, but SVD works also, because SVD is U lambda V. So if you call this R, you still have a unitary matrix on something else. So you can use also SVD. On actually SVD, you can do it both ways. You can send it to the right or to the left, the environment. So you do SVD, you compress, and then you put the orthogonal center to the next one, SVD, compress, all the way up. But first, you put it to canonical form with the center before compressing. If your MPS is not in canonical form, you don't want to compress anything. Okay? Good.
One sizes they start to diminish once they start compressing. For that, during the QR step, they are the same.
Sometimes, if you have exactly something of rank 3, QR, we actually you can get the bond dimension, which actually goes down without compressing. Okay. If it is exactly of rank 3. Otherwise, if it is almost exactly, then you need to actually throw away the small singular values. Yep. So if your matrices are rank chi, pretty much everything you do with a matrix is chi to the 3. If you multiply two matrices, chi to the 3. If you SVD, QR, everything is chi to the 3. And if you have n qubits, you need to do it n times. So the cost is n chi cube. Yeah.
Or you compress, suppose you have a whole range, some characters is small, then cost is still n to the power 4. That's the fraction.
N to the power 4?
Every time chi is n. Oh, wait, no, that's the bond.
Bond dimension. So wait. So it's a question I had this morning actually from Angel, like at breakfast. Like when I explained the MPS where it comes from, I gave you the big vector, like the big state vector, and I said, okay, you could actually do a QR or an SVD of that, and then little by little you construct the MPS. This we do once in a lecture to explain why MPS exist. You never, ever do that in practice. Because as soon as you construct an exponentially large vector, you're doomed. That's it. You have paid an exponentially large price, right? So you don't want ever to have if chi is of order 2 to the power n over 2, no point of using MPS, right? So when we write the emulator, maybe later this afternoon, you always initiate your MPS. Actually, it will be a rank 1 MPS, so chi equal 1, because it's a product state, the initial state of the quantum computer. And you never, ever form the full state vector. Except maybe to check that your program is correct for 10 qubits once, you know. But that's the entire point of all this technology, is that you have these super large matrices or vectors, but you represent them in terms of a network of tensors, and you only work by updating the small tensors one after the other, never ever contracting the full thing. Okay? Good. So now we can, yes, exactly. We have everything we have everything we need. Now I can actually revisit the MPS emulator that we had. But now we are going to compress. It's a good thing because then you will have seen one more time, so that when you implement it, it will be a bit clearer. Right. Okay, so once again, now we have a quantum computer. We want to simulate it with MPS. So one, we have, let's say we start with everybody in 0, 0, 0, 0. Okay? So first thing we will do is we will create a list of tensors. The MPS is a list of 3-lex tensors. And initially, so all these tensors will be the same. So they like M, alpha, I, beta. Initially, they are just rank of that going to be 1. Rank of that is going to be 1. And so this is, so essentially I have M0, 0, 0 equal 1, and M0, 1, 0 equals 0. And you're going to, so your MPS is essentially M1, M2, N minus 1. No, N. A list of these tensors initiated that way. Actually, also the assignment for later today, for some of you. Okay, then I have my MPS. If I want to apply a 1-qubit gate, I don't need anything about canonical form or anything, because anyway, it's just a contraction. It doesn't affect anything that is done here. It doesn't change the rank. It doesn't create any entanglement. So this, you can just contract these two guys using the tensor dot routine, for instance, and that's it. But now if I want to apply 2-qubit gate, and I want to compress the state, I'm going to put the center on one of these two. It doesn't matter which one. Let's say this one. I contract these two guys. Then I contract these two guys. Okay. So I have now Q. But the order in which you do things in the middle, it doesn't really matter. You could also contract these two guys first, then this one, then this one. It's not a big deal. Q. Then I contract this. Cheating a bit today. Third day, I'm getting tired of drawing the same thing again and again. Okay? And now I need to compress. So I'm going to do an SVD of this guy. cutting here. Okay. So this is equal to Q, U, lambda, B, Q, again, it's a nice form, which is, you can really see this as a rows, columns. So I am allowed to compress this if I want. Okay, so then you keep only, so the chi biggest, on that it you get your compression. If you don't compress, it's still correct, but you may have something that increase in time. So there are two ways to control the compression. Either you can say, okay, I want to keep 5 singular values because you are really focused on your CPU times, like you want to control the cost of the simulation. Or maybe we do another simulation with 10 and another with 20 to see how things work. Or you can say, no, I only keep, remember that sum over the singular values alpha of lambda alpha square equal to 1. That's the norm of your vector. Just due to the fact that the vector has to be normalized all the time. So you can also say that, okay, you just keep this up to chi. But you say that the error that you make has to be smaller than epsilon. So then you control it with a tolerance. Say, okay, I just, whatever, the integral of what I'm throwing away must be smaller than 10 to the minus 10, for instance. 10 to the minus 10 is a good default choice. And then sometimes the bond dimension will be a bit bigger, a bit smaller. It may adjust. And, okay. Right. And the good thing is that this is my exact state that I want. Let me call it psi prime. So let's say I started from psi n. I did my gate. I should have gotten this, but instead I got psi n plus 1, which is this truncated. So if I'm interested in the fidelity of my truncation, so which is psi prime psi n plus 1, this is actually the scalar product of this with the truncated one. So this guy here is equal to that, which is equal to lambda tilde like this, because of all the telescopic simplification of the unitary matrices. And that is equal to sum over alpha equal 1 to chi of lambda alpha square. Right? So what I keep is my fidelity calculation. And directly relates the truncation to the actual fidelity. Okay? So now, you see that if you implement the MPS emulator that we had before, you only need to add the canonical form. And then you can have an approximate simulator. And if you decide that you keep an epsilon of 10 to minus 2, for instance. So I have this f here, actually. Let's say the fidelity will be more the square of this. And it will be like a f n plus 1. Fidelity out of this step. So I have my f n of the order of 1 minus epsilon, where epsilon is a tolerance that I set in the truncation. And now, what happens typically, and it's something you can check experimentally if you want in the numerics, but there are very strong arguments why, but it's cannot really prove it mathematically because you can construct some circuit for it. It's not correct. But most of the time, the fidelity of the full calculation, which is the psi that you get after n step over the exact one. So let's say if I call the psi prime is what I should have gotten. I did everything exactly. So this fidelity here, typically, it's a product of the fidelity per step. So then I should not use the same letter. Alpha equal 1 to n.
One question.
Yes.
When you drop these similar values, you change the normalization to scale.
Oh, yes, sorry. Yes. I forgot that point. Good point. Actually, I think I didn't say it in the notes. Exact in the note as well. So for those who didn't hear the question, you need to renormalize your state. So to make sure that the norm is still 1. You would truncate, but you still want something normalized.
The standard norm how to normalize ones make those ways where I have the matrix and the basis where do I do it from?
So you in this lambda, you just make sure that the sum is 1. Actually, do you need to do that? You could also not do it, and then you would get an error that you would actually observe in the normalization. Anyway, you are losing information. I'm not sure which probably I would normalize, but yes. So, okay, when I say it's always related to the total sum of all the lambda square. So in that sense, you always keep the normal. Even if you don't normalize it, you know the norm by just looking at the sum of all the singular values. Matter of choice. But I should probably add a line in the notes too. Okay, where was I? Yes, the point I wanted to make here is that so if you believe me with this, and you can almost prove it, this is 1 minus epsilon. It's 1 minus epsilon to the power of the number of gates, which is essentially exponential minus epsilon is small enough. I mean. So when you compress, you have a behavior that starts to look like a real quantum computer. If you put your tolerance to 1%, then typically you have the kind of fidelity that they have in quantum computers. And now if you want to compare, I mean, of course, 1% is very bad. I mean, you get, you get 20 layers, you get this 0.1% fidelity at the end, which is what Google got. So it's very bad if you want to know what's going to happen in a perfect quantum computer. But if you want to make resource estimate to see, okay, where are we going to see a real quantum advantage, for instance, it's actually very useful because it tells you like, okay, at this level of fidelity, I can still simulate my my quantum computer. So now you are on par with what you actually have in quantum computing. So when you compare simulations, you should not compare something which is correct with 15 digits with something that doesn't even have 1 digit. Well, that's the only thing I'm saying. Okay? You can play, yes? No. You get an error, but this error is not similar to the physical errors that you will get in quantum computers. So if you want to really emulate noise, you have to do something else. One easy way to emulate noise, so there are, first, there are various kind of noise. Look at so if you want to be close to the physics, you you need to know essentially what kind of system you have in mind. But for instance, one kind of noise is coherent errors. Like, I mean, you have a two-level system, it's processing, and you are doing your gate, but you are a bit too late when you start to apply the gate, so it has processed a little bit more than you expected, for instance. So this is going to be a small, so that corresponds to applying a rotation, small angle epsilon around the z-axis. That would be z times epsilon over 2, which is essentially 1 exponential minus epsilon here, 0, 0. So, for instance, you can apply a gate like that after each layer, and that would give you this, and with epsilon, a random number between, that would be a coherent noise. If you want to really mimic decoherence, then what you have to do is to have some of your qubits, which are the actual qubit of your quantum computers, and some that are the environment. Then you put some small control node gate, so not exactly control node, but for instance, a weak, something that you would get for a weak interaction. So it could be, for instance, one of the gate we have is control Z. Control Z is the same as control node, but on the Z-axis, and its matrix is like this. Now the corresponding error would be, instead of -1, just exponential minus I epsilon. Tiny bit of entanglement, but now between your qubit, so it could be between two of your qubits, because you don't control the coupling that well, or it could be between your qubit and an ancillary qubit that is not part of your qubit, but is actually the two-level system nearby. So, for instance, very nice experiments by Johann Popp. He had weird data, and eventually he understood that he had a TLS, a two-level system somewhere close to his transmon, that was actually an extra qubit, super coherent, and without knowing, he was actually untangling it and then getting the result back, and it took a while to actually understand what was going on. But you always have this kind of thing at a weak level. Question is how big. So you can do that. And if you really want to have a big system, then you need to, if you do that, the problem is that you need to almost double the number of qubits, qubits on the environment. You can also use Lindblad equation, which is a way to mimic the noise. The problem with Lindblad is that it's Markovian, which means that there is no memory in the environment. And it's nice for quantum computers, but real noise are not Markovian. And actually, when the environment has memory, it is when it starts to be very nasty. So if you look at the theory of quantum error correction, for instance, you realize that the errors that are considered are almost always what are called are Markovian errors. All the errors that have memory in time or space, they are called correlated errors in the theory of quantum error correction. And there is a handful of papers of them. maybe 10 papers in total, like 6,000 in total, maybe 50 on 30 on corrected errors. For two reasons. Why is that? Because it's hard to know exactly what to put in your theory. But the real reason is that as soon as you put that, you are in trouble with quantum correction doesn't work anymore on people. Okay, so that's it. We have so this algorithm now with compression. It's called TEBD. But TEBD is more for the Hamiltonian version. But the Hamiltonian version is almost exactly the same. You will see it will take me like 15 minutes to 10 minutes to do the Hamiltonian version. It's almost exactly the same. Time, evolution, bond decimation. All these names came before we started to realize that this could be put in the framework of tensor networks, so they have weird names. But TEBD is okay, essentially what we have seen. The first algorithm with a name. Okay, and yes, that's it. So now we can start with DMRG. Where I'm doing with time. Okay, still have half an hour before the break.
I need half an hour. I'm not sure if it was already discussed, but can you help me? The discussion about the Boston price prudential metrics. I realized that actually what you consider is a system where only one of the qubits couples between parties. Right?
No, I mean
Doesn't matter.
no. Yes and no. So if you want,
Qubit of course couples the other.
exactly.
But
So
now.
it's true that there is only a link like that, and there is no direct link like this. Yes. But for instance, you could let's say this actually is chi-square. Chi-square, I could actually degroup this into two guys of chi. And then maybe this one has a direct link like this. Like I did when I did remember this this thing I did for the apply the MPO for so you can have as much information that goes from here to here, but you have to go through this guy. So you are using part of the pipeline to transmit information. You can really think about this virtual bond about like pipes with wires, and you are using this to actually send information from one part of the system to the other. And so if you have a unique bond like this, then it's true that to send something here, you need to go through that, and that takes some of the bandwidth. And it would have been better to have a direct link. So for instance, for 2D systems, you have a 2D system, let's say a system like this. The NPS way of doing that would be to use a snake. That would be my NPS. But then it's actually a bit problematic because this guy actually physically talk to this guy, but actually to talk to this guy, it has to go all the way through this. For 3 by 3, it's fine, but for 10 by 10, it's problematic. Another possibility would have been to use this network. So now everybody is connected to his actual physical neighbor. So this is an MPS called the snake ordering. And this is called a PEPS for projective, S for state, P for projective, E for entangle, and the first one I can't remember. Okay, I mean, there are tons of other tensor networks, and you could also use trees.
Yeah, I guess my question was the statement seems to be that an arbitrary n-qubit density can be obtained by tracing out sort of single qubit environment.
Any state can be put in NPS form. The only question is how efficient it is to be computationally. Okay.
I want to have an arbitrary density matrix on an n-qubit. Arbitrary.
Okay.
And is the statement so that you can get it by considering arbitrary single qubit state coupled to that system and then tracing out that?
Yes. You can always
you can get any density.
Yes, if you have a density matrix, you could write it like this, for instance. Density matrix. You can always purify it. And purify it, in my case, means cutting into two like this. So then I have the purification of my density matrix, which means that you can consider some auxiliary quantum system for the rest. And then I can transform this into an MPS and that into an MPS if I want to.
Sure. The question is, what is the size of this auxiliary?
The size of what?
Size, the minimal size of this auxiliary.
Oh, the same number of qubits.
Oh, yeah.
If you want to purify a system, you need as many auxiliary qubits as you have. But that's nothing to do with NPS. Huh? No. No.
But this is wrong. I understand that.
Why not?
Yeah. Yeah.
Let's say this is my system, and this will be my auxiliary one. Yeah. And you want to trace out that.
Yeah.
The rank here is at most 2. Because this is a 2 times something matrix, and the rank of a 2 times something matrix is at most the minimum of the two size. Huh? So if you have a matrix which is of P times Q, its rank is smaller like the mean of P and Q. So depending on the level of entanglement, but now if this is pure, that you need only one. Actually, you don't even need any. If this is a rank 2 MPS, then you can actually, I mean, if it is you have only 2 values in your density matrix, and you need only 1 qubit, and so on. But okay, so n is the largest number of qubits that you need for purification, and then you need 0 if it is a pure state, and so on and so forth. Right? No, I think it's nice. It gives some context to the. And so there are people that spend their entire careers looking at this guy, for instance. The truth is, NPS is really the one that really works very well. It's so simple. Everything is in chi to the power cube. You can increase the bond dimension to very, very large numbers and so on. PEPs, I mean, they have some very interesting results in PEPs, with PEPs in 2D, but it's very hard. So it's very hard. You need to use all kind of tricks of approximations, and it's really like I mean, there are a handful of people that knows how to deal with PEPs on the planet, and it's super intensive in terms of computational resources. So but I mean, and anyway, to learn PEPs, you first need to learn MPS. There is one class of tensor network which is actually as easy as MPS. These are the trees. If you have an MPS that looks like that, for instance, sorry, tensor networks that looks like this. So no loops. Then you can, if you look at them in the eye for 10 minutes, you will see that everything I said, canonical form, all this TBD, all these things, apply to trees as well. This is an easy generalization, and it already gives quite a lot of nice things. But okay, the plan of this lecture is not to touch anything but MPS and PO. DMRG. So it's also, so we have an MPS. We apply a gate. One. So if we use TBD, then we are going to compress. Okay. But let's say I don't do anything so far. I just apply other gates. I mean, up here. A small circuit, not too deep, but a small circuit. Because maybe I'm going to, I have a gate here, I'm going to truncate, but maybe the next gate is actually removing the entanglement that I built in the first gate. For instance, I could have like, for instance, this followed by this. Which is identity, right? Control node square to 1. So if I truncate here, it's a bit silly because I lost information, and a bit later, actually I would have been able to. So TBD we truncate after every single step, right? Now we are going to build an algorithm where we can build a full circuit and then try to fit that with another MPS. So that's DMRG. We have something, and we want to find the best MPS that matches that globally. So after a single gate, we already have the answer, but after multiple gates, it's not clear yet. Okay. So. So this guy I call psi prime. This guy I call psi. Maybe psi n or whatever. And actually, this is the circuit times psi n, and this is actually what we will keep as psi n plus 1. And so, okay. So once again, this is DMRG, so density matrix renormalization group. The name also has nothing to do with tensor network. It comes from it was initially an extension of the NRG, so numerical renormalization group of Wilson. That's really NRG. You should know. It's really how quantum field theory, modern quantum field theory arrived. DMRG was initially an idea to solve some problems with energy. But the version I'm discussing now is for quantum circuit. But you will see that once you have understood this one, you need to modify a few things and you get the global picture. So all DMRG, they always work in the same way. We are going to start with a state here. Let's say random. Each of these guys is random, for instance. And then we are going to sweep through the tensors one by one. Let's say I'm considering this one. Each time we sweep, we make sure we bring as much information as we can on the guy that we are considering by moving the orthogonal center to the guy that we are going to optimize. And then we are going to optimize this one. So with respect to what? In this case, we are going to maximize psi prime, psi n plus 1. Square. So we want to find psi n plus 1 that maximize the overlap between the states that we should have. Okay? And we are not going to perform, and we are going to perform this optimization tensor by tensor. So each time all the tensors are fixed, except the one I am optimizing on. When it is optimized, I move to the next one, move the orthogonal center, optimize this one, go down, and then up, and down, a few sweeps, let's say 5, 6, and usually you see that nothing moves anymore. Your DMRG has converged. Okay? That's DMRG. So the only thing I need to explain now is how to calculate the optimum guy here, supposing that all the others are fixed. Okay? Well, same old, same old. Now you should start to get bored. Like I'm making the same drawings over and over with very few variations between each of them. Tomorrow will be different. So I need to calculate this f. And it's a scalar product, so let me just calculate not f, but let's say square root of f, just a scalar product, right? And it's just the initial state I had. My gate. And maybe I'm not going to use exactly the same gate, sorry. This circuit is supposed to be the same as this one. And then scalar product, so I have the guy here, star. The orthogonal center. This is a number. It's my overlap. Now let's write this overlap in terms of this guy. So this guy is, let's say this is alpha, beta, I. Let's call it M, I. No, actually, yes. Alpha, beta. No. Alpha, I, beta. The one I can contract the whole thing, right? So typically, again, you start from the top, you just proceed all the way to the one here, then you start from the bottom, and then you do whatever you think is best to get the whole thing. And you will find that this is equal to T alpha I beta M alpha I beta star. It's linear in this guy. On the T, okay, I'm going to do something nasty here. I give you 30 seconds to copy this. T alpha I beta is this. You do the overlap, you make a hole, just remove the tensor. This is actually the guy which multiplied by the other one is going to give you the. You just need to contract the whole thing. Okay. Now we are almost done. Probably it will be time. Oh no, I still have time. Good. Okay, so now I want to maximize F. So F is going to be T alpha I beta M alpha I beta star times complex conjugate. But there is one small thing I need to take into account. The state needs to be normalized, right? So I need to do that with a constraint that sum over alpha I beta of M I alpha beta square is equal to 1. Yes? Oh, no, sorry, that's mistake. I usually give them different letters so that I don't have to track the ordering. So for instance, Greek letters for bond indices and Latin letter for physical index. Does everyone in the room knows how to use Lagrange multipliers to minimize a function with a constraint? Raise your hand if you don't know. I mean, very quickly, but if you haven't seen that before, it's something you must have in your toolbox. So you have a function C of, let's say, x1, xd, so in some complicated space. You want to maximize it or minimize it, but you don't want to do it in the full space. You want to do it on a manifold. For instance, so you have some equation like f of x1 xd equals 0. For instance, so this could be you are maximizing on an ellipsoid. For instance, you have this equation. You want to stay on the ellipsoid, and you're not interested in the full 3D space, but only what happens in this 2D space. You want to maximize. You're going to do that with a Lagrange multiplier. If you remember your thermodynamics 101, you go from like energy to the free energy, or to the enthalpy or the free enthalpy. And what you are doing actually is exactly what I'm going to introduce now. So if you had no constraint, you would just look at the gradient equal to 0. But now, so you know that DC equal gradient with a small variation. But now you know that the small variation, they must be in such a way that df, which is df dxi equals 0. You stay on the manifold. That means that this guy, which now I'm going to write gradient of f, is perpendicular to dx. So you have your manifold, the gradient of f, so you always stay there. So now the new equation is not gradient of c equals 0, but gradient of c parallel to the gradient of f. Okay? Which is something like gradient of c equal gradient of f. Bottom line, you introduce this lambda, it's called your Lagrange multiplier, and we are going to minimize c minus lambda f. Okay? Very simple, very, very powerful. And now I have screwed up my board entirely. Doesn't matter. So I'm almost done. So now I'm going to minimize, essentially, so can call it C again, which is T alpha I beta M alpha I beta star, T alpha I beta star M alpha I beta, minus lambda M alpha I beta M alpha I beta star. So it's a quadratic form. I mean, we know how to minimize quadratic form. So essentially, you want to take derivative of C with respect to M alpha I beta star equals 0. And that tells me that, so essentially you cheat again. Ready? So this is just a number. It's just a number. So it means that M alpha I beta is essentially whatever some number times T alpha I beta. So I did the whole, I contracted everything, and my optimum M is actually the contracted thing. Okay? As easy as it gets. Because I put it in canonical form. So I have the constraint of the normalization is sum over M squared equal 1. If not, I would have had all kind of environment and it would have been I mean, you can also do it without that, but it's much more complex. Okay? Now, I need to calculate this alpha. So that's very simple. So let me call small f sum of alpha I beta T alpha I beta.
There's a problem with your quantifier. Well, I mean, but now you actually had an equation where something is equal to something times M squared minus something else times M squared. The minimum is actually that this M is here, which is unphysical, I understand, but there is something wrong with the algebra.
Let's see.
Your Lagrange multiplier different.
Oh, it's probably squared, yes.
It should not be M squared. M for some reason, but I can see why.
I see your point. Properly, yes, you're right. Properly, what I should have done is this minus 1 squared. I want to push the constraint to be.
It would be a homogeneous.
Yeah. I need to check the notes. I know that the one are, yeah.
Or they-
Yeah, probably. But the result is correct.
Yeah. Nobody else. Yeah.
There's a lot of things to digest, huh? Okay. Where was I? Okay. So now if I calculate this number, and I know that the sum of m alpha I beta square is going to be to 1. I just so I need alpha equal 1 over square root of f. Okay, so this guy is 1 over square root of f, where f is the sum of square of this contracted tensor. And now, if I want to calculate big F, which is P alpha I beta M alpha I beta star squared, really the fidelity, then this is actually 1 over square root of f times f, the whole thing squared. So it's actually small f. So if I take the norm of this tensor, which I get with the whole, it is actually the fidelity of the operation.
What would the argument for the say alpha equal 1 over square?
Norm of sum of over alpha I beta of m alpha I beta square is 1. That's a normalization of your state. So I just calculate the normalization of t, and you get the normalization of. Okay, so to summarize, we sweep over the different tensors. Each time we put the canonical center, orthogonal center there by putting some QR. Then we contract everything but the tensor we want to optimize. And that's it. We just update. This tensor is our new tensor up to the normalization. We just update this tensor and we go to the next one. And each time you do that, you can calculate this f, which is the current fidelity of this thing. And as you sweep, you will see that f goes up. And eventually it's saturate. Whatever fidelity you can get with the bond dimension that you are currently considering. Okay? It's time for a break. So after the break, I will tell you a couple of slight improvements you can do with respect to that. The problem with this algorithm that we have right now is that the bond dimension is stuck. I just sweep, I update, but always with the same bond dimension. And you want an algorithm that allows you to actually increase the bond dimension up to the tolerance, the fidelity that you have targeted. So I will explain you that after the break. And then we can leave quantum computing. We can start to do some many-body physics a little bit. Okay. So we reconvene in 15 minutes. Again? Time? Yes. So to summarize the DMRG, you first initialize your MPS. So far, we have two options. First option is that we do a TBD. So we already have a good starting point. Or we just take a random MPS, you just pick up anything you want, each of the state at random. Each of the tensor, use numpy at random, and you get a random MPS. If you start with, and then you loop over sweeps So one sweep is when you go through all tensors. And for each sweep, you loop over each tensor. For each tensor, you first put the orthogonal center at the corresponding position. Then you optimize the corresponding tensor by contracting everything else. And you calculate the fidelity, which is just calculating the square of this, the norm of this tensor. And you should see the fidelity going towards something. And if you started with a TBD, probably it will start with something better and it will converge faster. If you start with something completely random, then fidelity will be close to 0 initially, and then you will need a bit more sweeps to get to the correct solution. You could use this algorithm, for instance, to do MPO-MPS product. You have an MPO-MPS. MPO-MPS product. So this is your MPS, your MPO, sorry. This is your MPS. What you want is find the best approximation of that. So it's exactly the same problem, except that instead of a quantum circuit here, now you have a MPO, but it's just, it doesn't matter what is the tensor network you have in the middle. Okay? So if you remember when we saw the zip-up algorithm to do MPO-MPS, we were doing everything with QR. You can just look at this algorithm again and replace QR by SVD, and you can truncate. That's one way to do it. Make sure that you start in canonical form. Or you could just start with something random and then just calculate the scalar product of that and remove one guy, contract, and get the DMRG version. Okay? If you take the best code available, typically they do both. You do first a zip up to get a decent approximation, and then a couple of sweeps with DMRG to converge to the best you can with this bond dimension that you gave yourself. Okay? As I said, I have still two problems. I mean, one problem, two possible solutions. So the problem is that here, the bond dimension, for instance, of this guy, let's say it's chi here, and 2 here. When I compute the T tensors, so I get this, and I make a hole here, but the dimension of these legs are the same. They are this still chi, and 2. So there is no way I can make my bond dimension grow. Okay? So the standard solution to that, so the DMRG we have seen so far is called one-site DMRG. The standard DMRG is actually the two-site DMRG, which I'm going to explain now. Two sites. Again, I have my initial MPS, some sort of quantum circuit. Getting easier by the hour. And then I want to optimize this thing. I put the canonical center, let's say here. So in two sides, what we do is we contract these two guys. We contract these two guys, so now we have something which is not an MPS, but something like that. So I have this state. okay, which we can still view as an MPS. Choose these two guys, so it's still an MPS, but for where one physical leg corresponds to 2 qubits. It's a bigger tensor. It was before it was chi by chi. Actually, when I say chi by chi, it should be understood chi by chi prime. I mean, the bond dimension typically varies a little on here. Before it was chi by 2. Now it's chi by 4. 2 here and 2 here. So I optimize two sites at the same time. So since it is an MPS, I can write that. Okay, let me stop erasing because you you won't understand anything if I do that too much. I have my quantum circuit. I have these guys. I have 2 here. This is a canonical form, so these guys are unitary matrices. So if I want, I can just consider this as flattened. And then I can apply the exact same algorithm as before. So the optimum guy up to the normalization is equal to this guy. Two sites is actually the standard. Some people tried 3 sites. It doesn't bring much. But 2 sites is a... So I have this, I have the optimum one. Then this guy, I do an SVD. And now, during the SVD, I can do the opposite of compression. I can allow, now this guy can actually have at most chi times 2, so 2 chi singular values. So I can allow the bond dimension to increase now. That's how I actually get more expressive, and that's. So I just keep more singular values. And then I have my new MPS now. This is lambda. Yes. So that would be the U on the V or the V on the U. Now, if I'm going up, so let's say, so I was optimizing these 2 guys. Now maybe I will want to go up, so optimize the next 2. But each time I move. So if I optimize these 2, next I optimize these 2. I always move by only 1, right? And then 1, and then I go down. Okay. So if I do that, then I will actually swallow the lambda up, and this one will be now unitary. So I'm still I'm moving automatically my orthogonal center in the process. Yes.
The reason I want to do the one exercise to get this ability to use the lambda or going to an SVD.
To increase my bond dimension. Yes. It can only be better because now I am optimizing more parameters at the same time. So in principle, you could get stuck in local minimum. But if you're optimizing 2, then you're exploring a bigger space. So there is a large chance that you get stuck in the local minimum. But the biggest importance, the most important thing is that you allow your bond dimension to grow. So you can really start from, 1 and let it grow until it has converged to the given fidelity. Each time you actually have the fidelity of the exact with respect to AMPS. So you could give yourself a tolerance and you increase bond dimension until you have 6 digits, 7 digits. You could do that. Sometimes you won't be able to do it because the bond dimension will become like 5,000 and then you will be have the computational power, but in principle you can control. Yes?
The way approximate quantum data, you kind of get equation of each step, whereas in DMRG you do it after
Few steps.
after a few steps. How do you define it?
Up to you. The deeper your circuit, the harder it will be to contract it. So there is an optimum in terms of computational.
What I go on diagram?
So actually, the quantum circuit, this algorithm has not been used by many people. Essentially, that was mostly myself for quantum supremacy experiments and a few other people afterward. So it's not something that is used a lot. On the other hand, the version to do NPO, NPS is used every day by everyone. Then it's just a single layer. And you will see when I introduce DMRG for, I mean, you will see that all DMRGs look the same. Like I introduced it this way because I thought it felt, I mean, it was good for the narrative of respect to quantum computing. But and in that case, yeah, it was typically we wanted to reach the highest fidelity. I mean, we wanted to reach a fidelity as good as the experiment and see how costly it was experimentally, numerically. That was the goal in this particular calculation. So it depends a lot on the circuit. So if you take the quantum supremacy experiment of 2019, we could get 1 amplitude on a laptop with the same fidelity as they had. And it was the hardest. And as soon as you turn to actually an actual algorithm, so we tried, for instance, QAOA, so which is some sort of quantum annealing, but with gates. And then suddenly we could get gain 3 orders of magnitude in the fidelity for the same cost. 3, 4. So as soon as you, I mean, really, it depends a lot on the quantum supremacy experiment was really designed to be super tough to simulate, and that was it. But as soon as you take something useful, quantum Fourier transform is trivial. It's around 10 MPO. Okay. So as this I will explain later when we do partial differential equation. You can quantum Fourier transform anything you want, and we do it routinely to solve PDEs. No, because the first part of the Shor algorithm actually generates a lot of entanglement. The second part of the quantum Fourier transform is very easy. The first part is, but there is a guy, Montaguero, now that in Italy, like in Trieste, he claims that he can do Shor in polynomial time. The guy is a reasonable guy. I mean, but I didn't check the calculations. But it might very well be that there is no reason to believe that RSA, I mean, factoring is actually hard. It does not belong to any of the complexity class where we know a lot of things and we believe it's really hard. It's alone in its class. It's just that we don't know of any good algorithm for factorizing numbers, but there is no, the theory was very weak. Okay, it's fine now anyway. Any computer which has been updated in the last 2 years now is post RSA. So even if someone builds a quantum computer, you're fine. You can still go on your bank account. Post quantum, as they say. Not really post quantum because we never had the quantum, but it's resilient. So factoring was really is a single in this class. There was 3 algorithms in the same class, 2 left to P, so two left. Okay. Yes, two sides. Is it clear, two sides? Every DMRG come in these two flavors, and you see it's actually the same thing, just you can consider two sides as one, and then SVD, or one after zero. Okay. There is a way to do to increase the rank within one site, and I'm going to explain it now, but I don't recommend it. I recommend to do two sites in practice. To be a bit complete. And after that, we can leave quantum computers. Pick up them. So it's a process known as enrichment. So when you do you put your state in a canonical form. So remember, you have your state. You cut here, put the Q here, the R here. You have the Q. The R you swallow in the next. Let's say we target this guy, for instance. Now, the next step is to do QR here, the Q here, and the R here. Then there is a small subtlety. So you have this guy here, M, alpha I, beta, alpha I, beta. So you just consider it as a matrix with alpha I grouped, and you do the QR. Q alpha I, some index A, R, A, beta. And so this is a typically matrix which is like this. Typically, you would write it like that. However, this is a size P. Okay, on this Q is chi, on Q. Here you don't have a full basis of the state of dimension P. But there is nothing that prevents you from actually writing a full basis. So instead of doing that, you can actually complete the basis. So here a P times P. You just have whatever QR gives you, plus you continue to have a full basis. And then the R will be whatever, like this, a lot of zeros. It will still be like that, and the rest will be zeros. And so if you look at NumPy, there is an option to get, I think the default is to get the stuff on the left. You want to get the minimum size, but you can continue until the full basis. Right? So this is called enrichment. You just add more vectors, and this will be, okay, and if you do that, here, now, here, I have my Q here. Now this Q here has a much fatter index here, with the R, which is mostly made of zeros. But it's okay because the R will never show up. When I optimize, it doesn't matter what is the R. Actually, I don't need the R. Right? So I can do this arrangement. I can do the same thing here also. So, and I will have a fatter things here where I have actually more states. And that allows to increase the rank. It's called enrichment. It also works. It's a bit more tricky to master. So get started with two-side DMRG, and then it's at some point you need to optimize your framework. Maybe you can try that. Okay, that's it. We are done with quantum computers first. We have emulated in every possible way using tensor networks. I mean, there are other techniques, and well, actually, even using tensor networks, there are other techniques. So, but you get the flavor. I mean, if you pick up a paper on quantum computer simulation using tensor network, you should be able to find your way. If it's not something that you have seen, it's a cousin or an extension to more complex tensor network or something like that. And I think we have also pretty much seen all the basics operations. Essentially, everything boils down to some sort of DMRG or some canonical forms. And now we can start to play around on actually solve stuff with that. Okay. So now I want to switch to actually where all these things started, which means to solve quantum Lie-Body problem. And so the quantum Lie-Body problem I want to solve is called the transverse field Ising model. I picked up this one for several reasons. One of them is that I did not need to introduce fermionic operators because half of the time there is at least a quarter of the room that doesn't know really well second quantization, and then they get lost. So that was a technical aspect. Also because it allows me to stay in the framework of quantum computing. I mean, these transverse Isings, they are essentially some sort of weak version of quantum computer. I will explain a bit why. And essentially, they give me everything I need to explain this algorithm. So why looking for more complex? It's the simplest of the many-body problem, right? It's really you can also attack it with quantum Monte Carlo. It's fermion free, so there is no sign problem in it. So I would say it's a good starting point. Okay, so transverse field Ising. Now we have an Hamiltonian. Let's get rid of all these unitary matrices. We have n spins now. And so the first thing we have is Ising interaction. These are the Pauli matrices again. So it means that if spin I and j, I mean, j can be positive, then it's antifermatic interaction, or negative, then it's Aij positive antiferromagnetic. Aij negative, it's ferromagnetic interaction. I can add a Zeeman field. It doesn't depend on the side. So at this stage, it's a purely classical model, right? If I just take I just take a configuration S, so state S equal up, down, down, for instance, like this. You can also move to 0 and 1 if you want to stick to qubit notation. I mean, up would be 0, and down would be 1. The same thing. This is the diagonal state of that. This thing is diagonal in this thing, so it's a classical problem. And we are going to make it quantum by adding a transverse field. right? Without the last term, it's
Even the Rudolph field, I mean, if you take field 0, it goes back to 1. Because let's take a permanent solution, there are two solutions there, all spins are up, all spins are down.
yes, that I.
But the quantum version also have to
Yes, okay.
all up, all down.
Kind of, except that if you. No, but okay, yes and no. In the sense that all these things will get spontaneous symmetry breaking.
Yeah, that's quantum version.
It does. I mean, the ground state, if you look at the ground, if you have the, no, of course, you can create any superposition and look at the quantum evolution. In that sense, even the classical version is quantum if you want, if you start with something which is superposition. But if you look at the ground state, it has the same property.
No, the quantum ground state of anti-permanent case is a superposition which you don't have.
No, but again, if any infinitely small staggering field is going to break,
Sure.
as in the classical case.
Yeah, but that's.
You're correct mathematically, but physically you're wrong. You see what I mean? Like physically, there is a single ground state. But okay, let's not. The point is that you don't need to diagonalize a big matrix to know the state of this thing, because you have the eigenstates, they are just classical states. And as soon as you switch on this guy, then we are in a different world. So why is this related to quantum computing? Essentially, we know the ground state in the large H limit, right? When H is large, the ground state, it goes to, so it's going to be aligned with this guy. So essentially it goes to up plus down over square root of 2 times the same thing over and over. So you go to the eigenstate of the X operator. And the energy is minus Hx number of qubits of spins. That's it. So you know the state, you know the ground state at large Hx. So you could prepare this state. It's a trivial state. It has no entanglement. It's a tensorial product. And the idea of quantum annealing is that if you decrease Hx very slowly, you're going to stay in the ground state. And eventually, at some point, Hx is 0, and you end up in the ground state of the Ising model. Okay, so it's called quantum annealing because it's a counterpart of thermal annealing, which will be classical annealing. Classical annealing would be you start at high temperature, you cool down, so you have for the classical problem, so you have a density matrix, probability, which is just Boltzmann weight, so exponential minus energy of the classical state divided by kT. You cool down the temperature, and eventually you end up in one of the ground states, if there are several, with probability 1. If you cool down slow enough that things are time to equivalent. Here, quantum annealing is the same thing, but now you just switch off the transverse field. Why are some people interested in that? Because finding the ground state of this guy is hard. As soon as you have frustration, so of course, if you just take a simple lattice, so if you take a lattice, a square lattice, and for instance, the coupling is ferromagnetic, then the ground state is just this. Or the one where you switch all the spins. If the coupling is antiferromagnetic, then you get this guy. The antiferromagnetic ground state. But already as soon as you have, let's say, for instance, 3 sides with a triangular lattice, antifermatic coupling, then if this one is up, then you want to put this one down. And this one is frustrated because he would like to be anti-aligned with both, and it can't. Right? Okay, for 3 sides, you can probably figure out what to do. But if you have a large number of sides, what is the optimum of this is actually NP-complete problem. So it's a class of problem which is supposed to be super tough. Super tough in general. Then for a particular matrix Gij, you may find, if it's like this, you may find very easily the ground state. But if you have no information, it's actually a tough problem. And you can map pretty much every problem of discrete optimization into finding the optimum of some Ising model. You've heard about 3-SAT, or if you are in all the discrete optimization problems that applied mathematicians formulate, you can map them onto that. Sometimes you need some extra ancillary spins. For instance, if you have a constraint where 3 guys need to be 1, for instance, but here you have only 2 sides interaction, then I would say, okay, it needs to be the same as this, but also this one needs to be the same as this, so you need to add more terms in your Hamiltonian. So it makes the mapping a bit more complex. But you can pretty much map everything onto this problem. To be honest, I have tried, everybody says that. When you talk to people in the industry, they all tell you, yeah, it's a tough problem, and it's very important for the industry. We could, for instance, you want to optimize logistic, you could maybe have less warehouses, or optimize the railway, you could have, maybe less stations, or. But I tried to ask people to give me actual problems that they can't solve right now with the algorithms they have, or that they are of interest to them. And so far, nobody gave me anything. So it's not exactly clear whether how really important it is in practice, or where are the current limitations. Because we have a lot of heuristics, a lot of classical algorithms, nothing to do with tensor networks or anything, just people have just been smart about finding algorithms to optimize these things. When people say it's NP-complete, it means that you don't have guarantees that your algorithm will give you the optimum. It doesn't mean that the algorithm is not very good, and it will work, and maybe it will work very well for a subclass of these matrices, or not so well for others. But the question is, people in the industry in particular are interested in actually what you get in practice, how many warehouses you actually have to build. And I couldn't put my paw on actual problems like that so far. Anyway, it's not the problem that we are interested in. The problem we are interested in is, first, can we get the ground state of this guy with some sort of DMRG? Can we do the time evolution of this guy, with quantum time evolution of this guy, with some sort of TBD? Stuff like that. So can we actually use our framework to do that? Question, of course, is yes. We will focus on the 1D nearest neighbor, especially when you implement this thing. I hope we will be able to go up to the time where we will be able to implement this thing with MPS during the hands-on session. Then we just do 1D. Very hard to generalize. The bond dimension may increase when you generalize. For instance, in 2D, the algorithm we are going to explain now doesn't work that well. Kind of work, but it's very expensive. There are much better ones. All right. Forget something? Yes. Going to bring back the skeptic in me one last time. So I'd like to discuss this quantum annealing just for 5 minutes. Is it a good idea to switch off this field? Honestly, to me, it's not clear. This is Hx, and this is a spectrum. So this is energy. So I said the ground state is essentially minus Hx times n at large h. At 0, it's something. And essentially, the ground state is going to look like this, for instance. For instance. The upper part of the spectrum, and this is, let's say, for 1D, for instance, you have n minus 1 couplings. So it will be n minus 1 minus. Let's say it's antiferromatic, for instance, and this would be the antiferromatic ground state. And then here you will have the ferromatic ground state. It has the same energy but reverse. And goes like n. At the end, up minus down over square root of 2 tensor. And there are tons of states in the middle. We have an exponentially large matrix. There are 2 to the n states. And they may look like this, for instance. Like maybe you get something like this. I mean, you have to understand you have an exponential number of them. Like this, for instance. Right? So what's going to happen? And so we are essentially solving I dt of psi equal h of t. Psi means the quantum computer is supposed to do that. And h of t is h of hx equals 0. Minus hx of t sum over I of xi. You just cool down your transverse speed in some way that you decide. So let me look at what happened here. I'm just going to look at 2 levels. And it's called the Landau-Zener problem. And I'm not going to solve it. It's in Landau book, so it's everywhere. Just I want to give you the glimpse of what happens. So you have one state, and you have a second state, the ground state, the first excited state, and you have a gap in between, which is delta. So if you go very slowly, and this is hx. If you go very slowly, you are going to stay on the ground state. That's the adiabatic theorem. So, but if you go very fast, so typically the problem that people look at, Landau looked at was Vt to t's time minus Vt on delta on the RW. So at t equals 0, you are here. And the question is to solve the time-dependent problem where V, it can be slow, as this, or large. If V is very large, essentially you just ignore the delta, and you just stay on your branch. Continue like that. So really the question is whether dHx over dt, the rate at which you're varying the transverse field, is it small with respect to, so this is an energy square, h bar equal to 1. So is it small or not with respect to the gap? If it is small, but again, this is Landau-Zener problem. You can just, I don't want to actually derive it because it would take another. Very well known, and you have extension of this problem where you are linked to a continuum, and there are tons of things. So, bottom line, if you want to stay on the ground state, you need to be slow with respect to this gap. Bad news is that as soon as the problem is actually difficult to solve, this gap is typically of order 1/2 to the n. It becomes exponentially small. So you have to be exponentially slow. So be very, very careful when you hear statements about quantum annealing. There are no reasons to believe that it should bring any quantum speedup. Maybe in practice it can be of some use because, I don't know, the time scales are better in favor. But Shor algorithm, yes, it's super tough to build the computer. But if we could, we don't know how to factorize this number as efficiently with a classical one. This, honestly, so you have essentially two companies that have proposed this. One is D-Wave. What about D-Wave? They have this transmon-based circuit based on quantum annealing. Okay. And then the second company is Pascal. These are based on Rydberg atoms. And the platform is nice. So the Rydberg atoms, if you don't know what they are, you just take an atom, you shine some laser beam on it, and then you make sure that the frequency is just below ionization frequency. So you get a very big atom in n equal let's say 60. So you start from ground state n equal 1. You go to n equal 60, 80, something like that. And you have suddenly a gigantic atom of the size of a micron or so. And you can do that coherently. So you can really, and then you actually you can put these atoms in tweezers. So you can actually put them one here, one there on select a location. And you get the interaction. So the Zi, actually is a Coulomb repulsion that you have between two atoms when they are both in Rydberg, because they are both big, so they actually repel each other. So Gij is actually for Rydberg atoms 1/r distance between the two atoms to the power 6. Wonder why 6? Because it's dipole, but there is no actual dipole because these things are neutral. So dipole will be 1/r3. There are no dipoles, so it's only second order perturbation theory that gives you the interaction. So it's R6. And this is how they get these things. And the Hz and Hx they get by just detuning the lasers. They can get about 100 of these atoms. So same problem as D-Wave, like the quantum annealing has no reason to be super efficient. It's even harder in the sense that they can't engineer any matrix Gij they want. They can only engineer what you can get by just positioning the atoms. But the physics is extremely nice. So this is at least interesting in its own sake. Okay, I think that's all I wanted to say about this model before. Yes. Before starting. So now we need to extend the TBD and DMRG on this guy. We do TBD. Which one do we? Okay, yes. Maybe I will switch the order with respect to the notes. I will do TBD first because TBD is trivial. So let's do TBD. So we essentially have an initial state. Let's suppose it's a product state. So whatever. We start like this, for instance. So we know how to prepare an NPS for that. And we want to solve the Schrödinger equations. Now we switch on the transverse field. that it's not trivial, and we want to switch to do. So one way to do that is just to use Trotter decomposition. So for instance, we have so H, or I erased H already, but if I write H as the sum of the classical terms on the transverse term, right? Then what I want to have is, so I want to write the evolution operator, which I can decompose the power whatever over epsilon. So I decompose it into small time steps. And then I can use Trotter approximation of this guy. So you can write it Trotter. If you've seen it, you can Google it. I'm not going to. So it's exponentially. So the first order one is just it's just this. To a correction of order square. You can do actually, for the same cost, you can do something better. This first order. Second order. But if you look at the second order one, when you take it to the power n, x epsilon. I take that to the power number of steps. This one combined with this one of the next with the previous. So it's actually exponential minus I hz epsilon over 2, exponential minus I hx epsilon, exponential minus I hv epsilon to the power t over epsilon. Then you correct for the last one, plus I hz. So you see, if you take the first one, you just need to correct at the beginning and at the end, and you get the third order one for the price of the second order. Okay. Right. Okay, so essentially, now we are almost done. If you look at exponential minus I, so x epsilon, well, this is just get the exponential of by 2 matrix. I mean, So it's sum over xi. This is actually the product over I, or exponential minus xi epsilon. They all commute this, the X matrices with each other. You just need to compute the exponential of the X matrix. So let me just give you a. So if you have the vector of Pauli matrix x, y, z, I want to compute exponential of this times any vector n times an angle theta over 2. That's actually equal to cosine theta identity plus I sine theta dot n. Try not to check it just by memory. But anyways, it's exponential of a 2 by 2 matrix. You can figure it out. Okay. Same thing. We will have the exponential of minus vi zj epsilon. This one is even easier because it's a diagonal matrix. It's going to be exponential minus I epsilon, exponential plus I epsilon, exponential plus I epsilon, exponential minus I epsilon. Exponential of a 2 by 2 matrix and factorizes also. So what I'm trying to say, but I didn't say yet, that you have your HZ things, and you have the essentially the you have essentially gates for all the interactions. And they all commute with each other. For instance, you can put them like that. The Zeeman term is another gate. Act on each qubit. Here you're just using nearest neighbor. And then you have to apply the gates on the x-axis, so different one. Minus Ix epsilon. And repeat. We have mapped the problem onto a quantum circuit. Approximately, you need to take epsilon steps, so you will make a small error. If you want to increase the precision, you need to put more steps with a smaller time. So this is the true TEBD algorithm. If you take this circuit and you apply the algorithm we designed for the approximate TEBD we designed for quantum circuit, you are actually doing the time evolution of your transverse Ising model. And that's actually one way to do it, the proper way to do it actually for this model to get the evolution. Okay, so we have mapped the problem back to a quantum circuit. We have questions at this time. Like I didn't stop for questions so far. I should. Is everything crystal clear or starting to get foggy? So far today we have essentially started to use this compression to extend the NPS algorithm we had to include the compression. And then now we know that we can actually use that to do the evolution of an actual Hamiltonian by mapping it to a quantum circuit using Trotter. That's one way, there are other ways. There are tons of ways to do the dynamics. Yes.
I'm kind of interested that the points that the matrix will quantum is actually that you are considering Hamiltonian I mean your Hamiltonian for
the Hamiltonian
or two of us
yes.
Then
You mean if you have three-level systems, for instance, what would you do? So on a classical computer, no problem. You can just do exactly the same thing, and your physical dimension would be 3 instead of 2, and that's it. So the simulation doesn't have any problem with that. The quantum computer, if you want to simulate spin 1 on a quantum computer, yes, it's a bit annoying. You can, but you will have. So one of the problems you will have is that some of the states you will use only a fraction of the states. So, for instance, you could use 2 qubits and say that -1 is 0, 0, 0 is 0, 1, 1 is 1, 0, and then 1, 1 I don't use. But if you do that, you see that any leakage to 1, 1 is going to be a problem. It's like so. I mean, people have considered it, and they have all kind of ideas. But I mean, let's face it. Even simulating spin 1/2 right doesn't really work very well right now. So they are still far from simulating spin wise.
the other point here is that the reason why you would not the problem the quantum computer was that you solved the problem that quantum computer solves, namely the abandonment
Exactly.
of system.
Yes.
You would have expectation value of the area.
Expectation value, the only way to solve that is to sample. And then you have a precision that goes as 1/3 of number of samples. So to solve, to calculate expectation value is actually costly in a quantum computer. You need to repeat the experiment typically 1,000,000 times to get anything. No, it's not easy to get something useful. Even if we had very, very good quantum computers, it's not easy to get something really useful out of it. The algorithm that we are going to explain next is the actual DMRG, so how to find the ground state of H. And that's easy for us, but it's very hard on a quantum computer. You could try quantum annealing, but then you would need to be very, very slow in going down. And there are some people who try to mimic some LibLab by adding extra qubits, ancilla qubits, to get some sort of environment, and trying to engineer some dissipation for the qubit that you are considering. I mean, very, very complex algorithms, but no real proof of anything in terms of speed of convergence or even. I mean, it's really tough. So getting the ground state or finite temperature is very, very hard on a quantum computer. Something I didn't say, okay, let me just give you, if you want the ground state, we are going to do it with DMRG. But I could just remove the I here and do imaginary time TBD. I just remove the I everywhere. Everything still works, Trotter works, everything works. And then I just applying exponential minus tau h on any state, and that's going to project it onto the ground state. So I will get my ground state. So imaginary time TBD is one way to get the ground state. We are going, DMRG is better, but this could work. Yeah. Any other question? 10 minutes left. I'm wondering whether I should get started. Okay, maybe I can get started on DMRG then. Okay. So we finally arrive at the true DMRG now. I won't have time to finish it, so I just want to give you the big picture, and then we fill out the details tomorrow. So I have H, my transverse field Ising model, and I want to find the ground state. In the form of an MPS, of course. Okay. Okay, so essentially I want to solve MPO MPS equal lambda MPS, an eigenvalue problem, where this guy is the Hamiltonian. Well, this guy I don't know, but it's my ground state. Same one as here. And this is the ground state energy. Okay, so for that, I need to solve two problems. The first one is I need to put H in the form of an MPO. H so far is not an MPO, it's actually given by the Ising model I gave you. So I need to put this in form of an MPO. And it can be done analytically. So we will just do it. Just look at it in the eye and what's the MPO? Rank 3 MPO. Very small bond dimension. So this is what we will do. So one, turn H to an MPO. And you will see when we do it. So I will do it for this particular example, but the way it works, you will see that essentially any local Hamiltonian where the interaction is local, you can turn it into a finite rank MPO. Okay. So okay, we will just do that. And then, well, we need to find a way to solve eigenvalue problems. And since we are only interested in the ground state, what we really going to do is we want to minimize psi H psi with psi an MPS. So we are going to essentially, if you minimize over all possible psi, then you get the actual ground state. If you minimize over all psi that are an MPS of rank up to this, then it's a variational approach. It's as good as your bond dimension. The good thing is that even if you didn't find the actual ground state, you have an upper bound for the ground state energy. Because it's variational, so you are at least an upper bound. Okay, and so this we can already see. I was just going to sketch it very quickly. So we have the state. Then we have the MPO for the Hamiltonian. Then we have the state again. Star. Right, so this is psi H psi, and this is a psi. Oh, sorry. I should have put the I should have put the stars on the other side. So you see that in terms of my tensors, it's a quadratic form. So for instance, this tensor appears twice, here and here. And so we will, the approach would be the same as we did for the previous DMRG. We will sweep over these tensors, optimize them one by one. When we optimize this one, we will make sure that we are in the canonical form with the orthogonal center here. And then we will see the optimization up amounts to actually solve an effective eigenvalue problem, but for a much, much smaller problem. We solve it, get the optimum, and turn to the next. Then again, we can do that with two sides or one side, with one side with or without enrichment. Two sides with enrichment if we wanted to. Essentially, that will be it. Okay, so that's it's not going to take us a lot of time. Yes. Yes. No, you optimize for both simultaneously. You really take the quadratic form. Yeah. We are going to do the details tomorrow. Yes. So to anticipate, you will have to. Let me give you the answer. But okay, you. So the problem we will have to solve to optimize for this guy here, the quadratic form, we will have to essentially diagonalize to find this you consider it as a vector, and you want to solve the following eigenvector problem. Or another way to see it, that you look at this, which you see as a matrix where alpha, beta, and I are the input, and alpha prime, beta prime, and I prime are the output of the matrix. You want to diagonalize this matrix and get its lowest eigenvalue. And that will be the best, the optimum value for the square. And then you could go to the next. So you see it will be almost the same as a DMRG for quantum circuit, except that at the moment where we do the optimization, we are optimizing for something different. So here it will be solving an eigenvalue problem. And we will have a third version later when we try to do solving linear problems. So solving from MPO times MPS equal MPS, where we will have to solve a small linear problem at the optimization step. If you have a good tensor network library, you can reuse most of the routine and only change this particular optimization step, depending on whether you are doing DMRG for getting the ground state, for solving a linear problem, for doing an MPO, MPS multiplication. To anticipate also a bit on what I'm going to say tomorrow, you see the point one is really crucial. So there are actually very few problems where you can turn the big matrix into a low rank MPO by hand. And this is why for 30 years, tensor networks have been essentially being used for solving problems like this, like getting the ground state of an Ising model, getting the ground state of a Hubbard model in 1D, Heisenberg model, these kind of models. So tomorrow, after we are done with DMRG, I will start to discuss tensor cross interpolation. And tensor cross interpolation allows you to turn pretty much anything into an MPO. Try, at least, if it's low rank. You give the structure, and if it's low rank, the algorithm is going to find the tensors. And then suddenly, it's like the sky is the limit. Like you can just revisit pretty much everything that has been done in applied math and just, okay, maybe I can do that faster with tensor network. That will be most of tomorrow will be on this TCI. TCI is tough. Make sure that you go to bed early. I mean, it's really twisted. It's very simple. It's a kind of algorithm where you look at it the first time, you think, no, I have such a big headache. But it's a good algorithm, and you know it because the more you look at it, the more clear it becomes. It's at some point it's transparent, and you just don't see how we could have done anything differently. But the first time you see it is a bit. So I will try to go slowly, and don't hesitate to stop me if you get lost, because I mean, it doesn't happen to at least half of you, and I don't know. Should ask questions about myself. I mean, it took me a while to get through that. So that will be the program for tomorrow, essentially. Finish this, then we will be done with, I would say, the standard tensor network techniques, and then learn about TCI, and then we will be on the. Then we will be not 30 years ago, but back to 4 years ago. Recent stuff. And then, so that will be tomorrow. And then the last lecture, we can start solving some PDEs with this thing. So start really applying it to totally different problems. Okay, are we good? Yes, it's exactly 1. So this afternoon, we continue. I'd like you to, I will be happy when I start to see plots on your screens. When you start to actually, okay, you have your simulator and you start to use it to compute something, and you plot whatever you want as a function of something else, and you experiment. If you get to that point, it will be already, I think, a small victory. And then those of you that are already there, you can already start to implement the MPS simulator. And you can just get directly with the compressed version. There's no reason to. Okay, so see you in 1 hour.